Pessoal, obrigado pelo retorno. Vai a última etapa da parte da manhã, são as apresentações. Professor, eu fiz o primeiro de uma vez. Então, eu vou passar uma apresentação rapidinho aqui, tá? Para falar depois. Professor Jorge, agradeço. Professor João, professor Renato. Praticamente em 5 minutos, não tem perguntas. Tá? A apresentação em português não concorre ao termo, as apresentações em inglês são avaliadas para concorrer. Tá? Então, o Sabir vai controlar a sequência que está na ficha e tem alguns itens para ser avaliado. Tá bom? Então, você quer falar lá para o Obrigado, Sabir.
Só precisamos que a gente pode bater 5 minutos. O aluno não precisa se preocupar, pode passar de 5 minutos. Só que vai ser retirado um ponto na hora de fazer toda a análise. Então, posso.
Good morning, everyone. My name is Lucas Alves, and today I'm going to present my work entitled Evaluation of Alkaline Hydrolysis Degradation of Hybrid Polyurethane Foams. Well, as you know, the environmental impact of polymers is a global concern. So to mitigate this, we replaced the polyol, the petrochemical polyol in the polyurethane synthesis by the oxypropylation of cellulose fibers under alkaline conditions, with the addition of propylene oxide to obtain a cellulose-based polyol. So after the obtain of the polyols from the oxypropylation, we synthesized a control foam with 100% of castor oil, and a moderation was with a slight excess of hydrogenate. And it was characterized by FTIR, XRD, SAM, surfraction, and alkaline hydrolysis tests. So we obtained basically 4 different types of polyols in the reactor with a temperature of 130 and 165 degrees Celsius, and the catalyst base used was potassium hydroxide and beta hydroxide. And for the polyurethane foam synthesis, we used 30% of desoxypropylate polyol and 7% of castor oil, with a slight excess of hydrogenate. So from the FTR, we can see the polyols were successfully prepared by the appearance of broad hydroxy stretching band, which are the active sites that can react with hydrogenates to produce polyurethane foams. Additionally, the SC results show a glass transition temperature between -31 and -47 degrees Celsius, which indicates a low monopolymer content. For the viscosity of the polyols, we can see that only the sample prepared with lithium hydroxide at 130 degrees Celsius showed the viscosity below 300, which is the limit application. And hydroxyl index showed very high values, which indicates the synthesis for rigid polyurethane foams. So now, for the FTIR of the polyurethane foams, we can see they were successfully prepared by the appearance of the characteristic bands such as C8 bonds, carbonyls, and CN bonds. Additionally, the XRD showed amorphous halo around 20 degrees, which indicates the pure polyurethane foam. For the SAM, we can see that all the samples show a similar structure compared to the control foam, but with larger pores in the hybrid foams. For the surfraction that measures the degree of pore leaking of the samples, we can see that by the addition of 30% of the oxypropylate polyol, it shows surfraction values around 5%, which indicates a higher degree of cross-linking. And for the alkaline hydrolysis tests, we can see that the castor oil foam showed a a linear degradation with a mass loss rate of 2.4% per day. It showed a weight loss around 7%, and it was statistically significant. But with the addition of 30% of non-propylene foil, the hybrid forms showed a mass loss rate around 0.30%, being 9 times lower than the control form, and they were not statistically significant. So only the castor oil forms really degraded. Conclusions, it was successfully prepared with the polyols and the polyurethanes, and by the addition of the oxypropylene polyol, it showed enhanced chemical stability and drastic reduction in degradation. That's my presentation. Thank you very much.
So good morning, everyone. I'm Fernanda Chile. I'm a doctor in nuclear engineer. I'm now working in CNP in Campinas, in Ariano. But this work I'm going to show is a collaborative work between IPEN Shoes in São Paulo, LGBTQ Grenoble France, and also FATEC Sorocaba. And I'm going to talk a little bit fast, but about the enhancing hydrophilicity and biodegradability of polymer non-composites with pineapple leaf nanocellulose. So in the field of sustainable material, we are working with pineapple leaves. Brazil is one of the most producing of pineapple in the entire world, and usually after the harvest they burn the leaves. So our idea is to use the leaves from the bottom of the plant to extract the cellulose and produce sustainable materials. So for the extraction of cellulose, we did the procedure is a simple procedure of alkaline and bleach treatment. And we also produce 2 types of nanocellulose, the CNF and the CNC. The CNF by ball mill mechanical processing, and the CNC by acid hydrolysis. And the main result here in the composition of the pineapple leaf fiber, we have the cellulose content that is 55%. It's even higher than hardwood and softwood as the most used to extract the cellulose. So this is a good result for this kind of source. And for the CNF extraction, we vary some kind of time during the ball mill. And in this time we have smaller particles. It cannot just be called CNF or just CNP, the cellulose nanoparticles, because it's too small. And also the CNC extraction will vary main conditions like temperature, time, acid concentration. And with lower temperatures and lower acid concentration, we have high yield and also smaller size length. So this is a good result. And when we use a higher acid concentration and temperature, we have a lot of degradation. And we use CNF to produce polymer non-composites. We use CNF because we have a lot of amount. CNC we have just a smaller content. So we blended with PLA and PBG, they are both biopolymers, and we vary 1 and 2% of CNF content. And in this image, we can see that when we increase the CNF content, we have an increase in the roughness and some irregularities because of the CNF. This is common when we use CNF. But in contact angle, we have a decrease in the contact angle, and this indicates that we have an increase in the hydrophilicity. And the main result here that I'm going to show is the biodegradation. We did the simulated soil for 6 months, and we can see that when we increase the content of CNF, we have an increase in degradation rate. So to conclude, we can see that we have a high potential. We have 55% of cellulose. We can produce CNF and CNCs, but we can be careful with the conditions. We can produce nanocomposites, and also we can do many applications with it. But we already published 2 types of articles with these results. And thank you for your attention. I would like to acknowledge my co-authors and from the agencies. Thank you.
Now it's my work. Yesterday it was not, but now it's my work. So hello everyone, my name is Samir. So I will tell something about tailoring chitosan to improve performance, the impact of alkoxy-methylene derivatives on crystal violet absorption. This is part of my doctorate, just the finish of my doctorate. And to start, I have modified chitosan with 3 kinds of alkoxy-methylene. The first one is a dual ester. That you can see that almost no change in the color after the modification. The second one is with 1 cyano group. Now you can see like a yellowish, brownish color of differentiation. And the third one is with 2 cyano groups. I'm trying to understand what kind of group in the chitosan can change in the absorption of the crystal violet. And you can see like a yellowish color. So I did zeta potential to analyze the charge near the surface when I change the pH, just to understand if the absorption will be affected by the change of the pH in my modified chitosan. So as you can see, and as Professor said, when we have lower pH, I'm using acetic medium, lower pH, we have a higher stability on chitosan. But on my derivative, I have like an unstable suspension. For the second one, it's the same thing. On acetic medium, of course, unstable on the lower pH. And the third one I did on aqueous medium because it was made in other plates. And you can see, because there is no acetic medium, we have always fluctuation independent of the pH. Maybe in higher pH you have like something unstable, but it's always fluctuation. So the experimental phase to test the absorption is use a solution of crystal violet. I use a buffer to maintain the pH. Add a clean absorbent, it was my chitosan, and remove that absorbent. And with the clear solution, I did some dilution. After that, some UV spectroscopy. And this is the color of my chitosan modified end of my absorption. As you can see, maybe by the color, the EM is like better than the CA and the EM. So the isotherms showed something incredible for us. For pH 5, using SIPS model, we can see the chitosan in here in black with a maximum absorption of 34 milligrams per gram of chitosan. But if you can see the other ones, the modified ones, will have a really high increase instead of here. It's about 59% for ECA and 527% for EM, the absorption, maximum absorption. For pH 7, we have a really high improvement. For chitosan, we have like a maximum of absorption of 8.5 grams. But for the EM, we have a maximum absorption of 382 milligrams per gram. What showed us 4,400% of improvement with this modification. The other one has improved as well. The DBM now is better. We don't know why yet. We're studying it. And as we can see, the higher the quantity of cyano groups in the modification, the higher is the absorption. And again, we still don't know why. We're studying it. So, in conclusion, zeta potential showed low suspension stability for all pH. So my chitosan is not soluble, not in water, not in acetic medium. I don't know what the would be soluble. And the lower stability, the easier it's recover and reuse. If I'm thinking about absorption, it's to recuperate this kind of material. The absorption test demonstrates great improvement. The higher the amount of cyano, as I said, the higher the absorption. And the maximum increase is 4,400%. And thank you, everyone, and everyone that helped me.
fazer minha apresentação em português. Vou apresentar para vocês os resultados parciais do meu trabalho de mestrado, intitulado, então, Celulose Bacteriana da Kombucha como hidrogel sustentável para a remediação ambiental. Dando uma introdução, então, durante esses anos, a crescente preocupação com o impacto ambiental, principalmente pelo extrativismo, vem procurando alternativas mais sustentáveis. E dentro dessas alternativas, a gente encontra os biopolímeros, que são materiais, né, de origem natural. Entre esses biopolímeros, a gente encontra, então, a celulose bacteriana, que vem ganhando aí um grande espaço ao longo desses 10 anos. E, devido a esse destaque que ela tem feito, existem formas de se produzir as formas tradicionais que a gente já conhece no laboratório, e também a gente pode produzir a celulose por resíduos industriais e resíduos agroindustriais. Dentre esses resíduos, durante a produção da celulose, ela produz ali um resíduo de valor agregado, que a gente denomina SCUB, e esse SCUB, ele é um subproduto da produção da kombucha. A kombucha, então, é um chá ali fermentado, ela tem origem no norte da China, na região da Manchúria, e ela era muito utilizada pelas suas propriedades medicinais. E essa kombucha, então, ela é um chá ali fermentado pela planta da Camellia sinensis e também por uma cultura simbiótica de bactérias bebeturas. Essa cultura a gente denomina o SCUB. A Camellia sinensis é tipicamente usada para a produção da kombucha, apenas bebidas produzidas através dessa planta, que é denominada kombucha. Outras fermentações, se não for realizada por ela, não pode ser chamada kombucha. Então, para a produção dela, normalmente se utiliza o chá verde e o chá preto, que já é derivado da Camellia sinensis. Bom, então, para produzir a nossa celulose, a gente vai precisar, então, da fermentação do chá verde, o açúcar. Nesse trabalho, eu utilizei 2 tipos de açúcar, o demerara e cristal, com 2 concentrações de 2,5 e 10. O SCUB, que é o que vai dar, junto com o start, que vai iniciar a nossa fermentação. Esse start, ele nada mais é que o próprio chá já fermentado ali, por mais de 30 dias, ele apresenta ali um pH mais ácido. E esse SCUB, que é a nossa cultura, que vai ser colocado ali tudo num recipiente de vidro, tem que ser de vidro, devido à produção dos ácidos e a própria fermentação acaba acontecendo. E aí, esse recipiente é armazenado ali, a gente cobre essa superfície com papel filme, um papel filtro ou um tecido, e fica ali por fermentação por 21 dias. Após esse processo fermentativo, a gente precisa realizar ali a purificação dessas membranas, onde é purificada com hidróxido de sódio por 1 hora a 80 graus, para a gente tirar qualquer resíduo da fermentação ali, das bactérias e do próprio chá. Após a produção da celulose, a gente realizou ali um planejamento fatorial, foi realizado um 2 a 3ª, onde a gente variou o tipo de açúcar, a concentração e os dias de fermentação, para a gente obter ali uma melhor resposta de espessura para a gente produzir os nossos hidrogéns. O nosso resultado deu que o que mais impacta a produção é o tipo de os dias, onde o melhor tempo ali é 21 dias, seguido do tipo de açúcar e as interações das três concentrações. Bom, seguido a gente partiu para a etapa da produção dos hidrogéis, onde foi realizado 2 métodos, sem e com desconstrução da membrana, onde a desconstrução foi realizada pela trituração delas, e foi feita a reticulação com carboximetilcelulose, uma solução de 2%, seguido da imersão dessas membranas no cloreto de cálcio. Tem um videozinho de como ficou esses hidrogéis. Após foi realizado, então, as caracterizações. Os picos característicos da celulose, aqui em 3.300, a partir do 6.000 a 900 a gente indica, né, a reticulação do CNC e o hidróxido de cloreto de cálcio na membrana. A PG, a gente percebe aqui uma baixa redução ali na sustentabilidade, pode ser devido à redução da cristabilidade e da cristabilidade devido à carboximetilação da CNC. E o MEV, a gente percebe que essa característica rugosa que apresenta é devido à estrutura morfológica da celulose. E a baixa presença de poros é devido à penetração do CMC na sua rede pilar da celulose. E os nossos resultados indicam, então, que essa proposta dos hidrogéis é viável pela nossa aplicação, que é a remediação ambiental. Obrigada.
Hi everyone, good morning. I'm Abdel from the Format Group at the University of Canada. I'm an undergraduate student, and my project focuses on interdistrict ambulance cascades hydrogel for drug delivery, supervised by Professor Dr. Manbaish. Well, the main object of my project is the development of a breathable hydrogel for drug delivery applications composed of hyaluronic acid that has a good compatibilities, gelatin to cross-link the final treated material with gelatin, a natural cross-linker, and cellulose crystals to increase the rheological properties. To prepare my hydrogel, I use magnetic sphere to mix the gelatin and a speed mixer to incorporate the cellulose crystals and the hyaluronic acid. But there is a problem, because not all hydrogel results on a printable material. Therefore, to identify the formulation, I carried out a factor design with 9 different samples, 10 the concentrations of the nanocrystals and gelatin to analyze the elastic modules called the brine and the cross point between the modules called the endpoint using a rheon. Through the analysis, I found that cellulose crystals are primarily responsible for neurologic response, increasing both the brine and the endpoint. And that's good because if I want to increase the neurologic response, I just need to add more nanocrystals. So I could discover how the nanocrystals interact with my hydrogel. And I also found interaction between gelatin and nanocrystals, indicated by the curvature of the contour plots. Now can we see in figure 4, and it's more visible in the endpoint response, as shown in figure 4b. So using the factor design results, I was able to establish ideal formulation of my hydrogel, and the subsequent rheological tests confirm that hydrogel has the characteristics of a printable material. For example, gel-like behavior, that means the hydrogel maintains elastic response over low to moderate shear stress until the shear stress becomes strong enough to disrupt. And a shear thinning and isotropic profile. In other words, the viscosity of hydrogel decreases with the increasing of the shear rate, but this hydrogel has the capability to increase your viscosity again. There is an issue. Well, all those things are saying that I was in the right way, but I need to confirm it. So I created the material, and that the material shows a good shapeability, a perfect printability index of 1 using this equation that analyzes the magnetic shape parts of the structure. And there's a video. That is a 3D view printer for tissue lab. And in conclusion, the factor design indicated shelf 5, CNC pen, and three formulations of the best virological properties, and the cellulose crystals are determinant for the virological values, and the indices showed a good shape to the lipids. That's it, my contribute and my substitution. Thanks so much, guys.
Então, bom dia a todos. Eu me chamo Isabela Torquato e eu vou apresentar um trabalho intitulado como Sistemas Transdérmicos para a Liberação Notificada de Fármacos na Medicina Veterinária. Tá? Então, como introdução, os efeitos adversos que a gente vê na prática clínica, eles se dão devido principalmente a desvios de administração convencionais que a gente utiliza, que é a via oral e a via subcutânea. Quando utilizamos os sistemas transdermais, conseguimos obter um aumento da biodisponibilidade desses fármacos e, consequentemente, uma redução da dose e frequência de administração, resultando, então, em menores efeitos adversos. A utilização de biopolímeros, como o hidroximetilcelulose, né, o HPLC, ele é amplamente utilizado nas tecnologias farmacêuticas, principalmente para desenvolvimento de dispositivos médicos. No presente trabalho, a gente utiliza o HPLC K4M e K5M. Então, o objetivo desse trabalho foi desenvolver diferentes sistemas transdérmicos para a liberação do opioide de metadona para uso veterinário. Então, na metodologia, nós desenvolvemos 4 formulações diferentes, sendo a formulação FA e FB, à base de hidroximetilcelulose 4M, nas concentrações de 1,5% e 3%, e as formulações C e D, com HPLC K100M, na concentração de 2% e 3%. Esses hidrogéis eles foram preparados, depois eles foram submetidos à técnica de secagem, a técnica de secagem, então eles foram submetidos tanto à temperatura ambiente quanto à temperatura controlada. Os filmes hidrogelatinosos obtidos, eles foram submetidos à avaliação de capacidade de entumecimento através do dispositivo de Esmin-Neff, né, onde os filmes eram colocados no funil sinterizado e era avaliado justamente a absorção da solução TC-199 para avaliar a capacidade de entumecimento desses filmes. Como resultados, na técnica de secagem, a gente observou que as formulações FA e FB, pela técnica de secagem na temperatura ambiente, elas apresentaram uma maior perda de água. Isso se deve ao fato, principalmente, relacionado a essas formulações terem sido utilizadas num peso molecular menor. Já na capacidade de entumecimento, então, a gente observou que a formulação FP, né, contendo principalmente o HPLC K4M a 3%, ele apresentou uma capacidade de absorção dessa solução TC-199 maior, que pode estar relacionado justamente a essa massa molecular menor e justamente inserida na composição. Então, como conclusão desses resultados dessas formulações, a gente observou que essas formulações elas apresentam um importante potencial para desenvolvimento, incorporação da metadona e desenvolvimento desses filmes hidrogelatinosos, esse sistema transdérmico. Muito obrigada.
Bom dia, pessoal. Vocês estão me ouvindo direitinho? Meu nome é Fabiana. Eu sou professora da Universidade Federal de Ouro Preto, a UFOP. E esse ano corrente de 2025, eu estou fazendo pós-doc no Instituto de Química da USP, São Carlos, sob supervisão da professora Elizabeth Frolino. Eu desenvolvo um projeto que é um pouco lá no São Carlos e um pouco aqui na UFSCar, com os professores Wagner e Jane. Hoje eu vou falar da determinação de amilose presente aí em diferentes tipos de amido, usando aí o método colorimétrico do complexo amilose iodo. Bom, o amido, ele é extremamente conhecido, usado aí, né, consumido aí desde os nossos primórdios. A gente sabe que nós temos aí diversos tipos, né, de fontes de amido, então, milho, batata, mandioca, e o amido, ele, então, é extremamente usado nas indústrias de diversas maneiras. Eu subdividi aqui em 3 tipos de indústrias, mas se a gente for, né, avaliar as utilizações do amido, elas são incontáveis. Então, vou classificar aqui as indústrias, por exemplo, de materiais, têxteis, e classificando aí uma importante utilização aí na indústria alimentícia, que é usado aí como gelatificante, espessante, aí nas diversas alimentos que nós temos, né? Seja de sopa, ele que dá aquela engrossadinha aí em diversos materiais, né? Em diversos alimentos que a gente consome. E é também bastante usado aí na produção de ração animal, na qual ele confere aí ajuda a dar aquela moldagem da ração e também formar aqueles pellets que né, a ração quando a gente compra, né, que tem aquele formato. Enfim, parte dessa ampla utilização do amido se deve às suas várias características intrínsecas, como origem natural, baixo custo, relativamente, né, baixo custo, ampla abundância e uma grande característica importante que é a biodegradabilidade, o que confere aí uma importante informação para as coisas, né, para o que o cenário mundial exige de materiais recicláveis. Recicláveis não, naturais, né, e de ampla utilização aí para degradação, de fácil degradação. Bom, parte da utilização do amido, né, da sua reatividade, se deve à presença de 2 polímeros principais, que é a amilose e a amilopectina. A amilose é um polímero, né, presente aí no amido, é um polímero de cadeia linear, já a amilopectina é um polímero que apresenta aí uma série de ramificações. Pensando nisso, o objetivo desse trabalho é uma quantificação, né, da amilose presente aí nos amidos comerciais. Esse trabalho é uma perninha do meu projeto e surgiu da necessidade que, para entender né, as minhas reações e os filmes que eu produzo, eu precisava da informação de quanto tinha de amilose e amilopectina. E a maioria dos fabricantes não nos fornece essa informação. Então, surgiu, né, eu até fiquei surpresa dele ser escolhido, né, para ser oral, porque é uma perninha do meu projeto, justamente, embora seja simples, ele não é menos importante pela necessidade de entendimentos das nossas reações. Então, basicamente, a amilose é que vai, né, nesse caso, nós vamos quantificar a amilose e, por diferença, a gente faz a amilopectina. Essa metodologia foi baseada aí num método de McFrance de 1998, com algumas modificações. E como que funcionou? A amilose, ela tem uma estrutura helicoidal de ligações alfa-1,4 que liga-se com as formas triiodeto e pentaiodeto e forma de imediato um complexo muito bonito de cor azul intensa. Esse complexo, então, formado, ele, né, com essa cor intensa, ele tem aí uma absorção aí em 620 nanômetros. Aqui, né, a gente está mostrando o formato aí da helicoidal da amilose, quando ela se liga automaticamente aí com as espécies triodeto e pentaiodeto, ela forma, então, esse complexo azul. A amilopectina, ela forma também um complexo, mas ele é muito fraco, a gente não consegue quantificar. E também a coloração é diferente. Então, o que a gente quantifica é a amilose. E aí, aqui, só para mostrar como que ficam os padrões, né? Bem coerentes com né, maiores concentrações de amilose, uma coloração azul mais intensa. Como que foi feito? Nós fizemos uma solução estoque de 5 miligramas por litro, a partir dela a gente fez os padrões. Paralelamente, a gente fez o reagente de Lugol, que é o reagente que tem as espécies penta e triodeto. A gente pegou 1 mililitro da solução estoque, 5 mililitros da solução de Lugol, diluiu-se para 35 e a gente fez, então, as soluções padrões, né, do complexo amilose iônico. As amostras de amido, nós trabalhamos com 4 amostras distintas, 2 de milho e 2 de batata, sendo 3 delas compradas como reagente químico e uma é um amido da indústria alimentícia. A gente pesou em torno de 100 miligramas dissolvidos em 10 mililitros de metilsulfóxido a 85 graus, né, aquecido a 85 graus. Depois, a amostra sofreu o mesmo processo dos padrões, ou seja, 1 mililitro de solução, 5 de Lugol, diluídos aí para 35 mililitros. Tanto o complexo quanto a amostra foram analisadas aí usando aí a ultravioleta, né, com comprimento de onda de 620 nanômetros. Também foi feito as análises de DRX, na qual a gente calculou a cristalinidade dos amidos. Bom, como resultados, a gente tem aí uma curva analítica que foi bem, vamos dizer assim, com um alto, né, coeficiente de determinação, com 3 noves aí, então tivemos uma curva excelente. Foi quantificado, determinado também o limite de detecção e de quantificação, e os valores de absorvâncias obtidos para a amilose foram, né, calculados através da curva analítica, na qual aqui a gente tem, né, o cálculo, então, da amilose, a amilopectina por diferença, e também o grau de cristalinidade obtido, né? Eu não trouxe aqui, pelo tempo, os gráficos de cristalinidade, mas eu tenho todos, então aqui só estou mostrando os resultados, na qual aí, gente, os 3, né, primeiros amidos, nós obtivemos uma quantidade maior de amilopectina. Todos que tiveram uma porcentagem maior de amilopectina também tiveram um grau de cristalinidade um pouco maior. E o que foi coerente com a literatura? Haja visto que, né, a literatura retrata que a cristalinidade é devido à organização das ramificações da amilopectina. Então, maior a amilopectina, maior a cristalinidade. Como conclusão, nós tivemos que os amidos, né, os 3 primeiros amidos ali abordados na tabela tiveram uma porcentagem similar de amilose. O amido 4 teve uma porcentagem maior. A cristalinidade foi coerente com o que a gente tem na literatura, então maior amilopectina, maior cristalinidade. E para um melhor entendimento dessa proporção amilose-amilopectina, nós pretendemos fazer mais um teste estrutural aí e também validar o método aí de acordo com o mapa. E a Anvisa, Inmetro, enfim, com os órgãos, né, que gerenciam isso. Obrigada. Com tanto carinho durante esse ano de 2025. Obrigada, né?
Hello everyone, my name is Danielle, and today I would like to share with you a little bit about the project I developed with Professor Danielle and Junior. Basically, we decided to create a self-healable hydrogel. The main difference between a regular hydrogel and a self-healable material is that when the self-healable suffers any physical damage, it can reassemble its structure. This property, it relies on the theoretical background of the dynamic covalent bonds. We chose to use amine and aldehyde groups to form imine groups that have this property of reassembling the structure. So when we combine these 2 materials, amine and aldehydes, we can have a spontaneous reestablishment of the chemical bonds. And this reestablishment will give you the property of the material be organized together again. So it is associated to self-healing properties, and it can guide you to long-life materials, and it has a very interesting application in the biomedical field when we think about wound dressings, for example, or some platform to drug delivery. Basically, in our study, we chose to use oxidized sodium alginate as an aldehyde source and the carboxymethylketosis as an amine source. The synthesis was pretty easy, to be honest. We mixed together oxidized sodium alginate and carboxymethylketosis. Homogenize it, and then we mold it into petri dishes to form the hydrogel in a spherical shape. We also synthesized one more sample, this one charged with calcium chloride to enhance the physical properties. And then we could have these two materials. Well, FTR spectrum, it showed two most important things. The disappearance of this peak in oxidized sodium alginate, it could prove that the oxidation really occurred, and the appearance of this peak in 1660, it showed that the imine bonding was formed. So, NMR analysis, it showed a new shift in 5.44, and it indicates hemiacetal formation, and it's related to the appearance of new peaks in sodium alginate. Well, talking about self-healing now, when we cut the sample into halves, when we put it together, it automatically could reassemble the structure. And it could be observed in the sample of gel and calcium and the gel by itself. And this self-healing, it was very fast. So it was possible to see that when the material was put together again, we couldn't see the physical damage anymore in both samples. Also, when we put the samples together, we can suspend them and they are not going to pull apart again. Another test we developed, it was the dye migration. So when we put the sample into parts and put them together again, the dye migrated between one part to another. And this is an indication of the self-healing of the material. So, in the conclusion, sodium alginate was successfully oxidized and it was evaluated by NMR analysis. This material was then used both as a cross-linker and copolymer in the gel and calcium samples. And this self-healing hydrogel using natural sources could be successfully synthesized, and the self-healing property was confirmed by dye migration and cutting tests. Thank you for watching.
Hi, good morning, everyone. My name is Giselle. I am from Pontifical Catholic University of São Paulo, and this is my project, characterization of 2D printing scaffolds based on poly-lactide lactide with try to situate for future meniscal application. The meniscal is essential for log distribution and joint stability. Is particularly susceptible to traumatic and degenerative injuries to its limited vascularization and mechanical stress exposure. Tissue engineering offers solution based on poly and lactide called lactide, PSLA, and blended with try to situate tech ions in material with enhanced printability, tissue-like porosity, and improved cell adhesion. Methodology: PLDLA mixed the tech at concentrations in 1% and 2%, dissolved in chloroform. Scaffolds de PLDLA of PLDLA, PLDLA tech 1% and PLDLA tech 2% were obtained by extrusion-based 3D printing. Chemical characterization has performed by FTIR. Thermal stability was evaluated by TGA. The thermal properties were analyzed by DSC. Results: FTR, the presence of the tech in the different formulations has confirmed through spectral deconvolution in spectral region. The analysis revealed the direct relationship between tech concentrations and the increase in spectral area, confirming the spectral proportional between the amount of resistor and the detect signal. This is tech, tech pure tech. This is PLDLA tech 1% and PLDLA tech 2%. DSC, it was demonstrated that tech reduces the glass transition temperature of the polylactic acid materials. This reduction is attributed to tech acting as the plasticizer of the PLDLA. TGA, the analysis revealed that an increase in tech concentration results in the decrease in the max of the PLDLA tech 1% and PLDLA tech 2%. Such effect is attributed to the volatilization of the tech practitioner, indicating that at low concentrations, tech did not promote an increase in the thermal resistance of PLDLA. I would like the PUC São Paulo, Materials Laboratory, CNPq.
And good morning for everyone. Firstly, I want to thank the event organization, YouthSCAR and COPS, both for the realization of the work and the opportunity to present it now today. I would also like to thank my co-authors, Guilherme Francisco Pegoraro, Giovanni Mirabete Cariello, and my advisor, Professor Giovanni Pimenta. Finally, my name is James Pereira. I'm an undergraduate student of chemistry here in YouthSCAR. The work we present today is the synthesis of SML2, zinc oxide, nanoparticles doped with zinc by Sol gel method. So, for the introduction, first we need to define what is nanotechnology. And in this case, we are talking about every and all material that are in the nanometric scale. It is actually a widely studied and widely disseminated area, and because of that, it is extremely important range for the economy and industry. And by that, I mean by the synthesis of material or the sale of a nanotechnological material itself. The student material in this work is tin oxide, SNL02, and it's not a random choice. It was because of tin oxide properties, mainly due to tin oxide semiconductors properties and its thermal and electrical stability. And SNO2 is not an isolated material, actually it's widely studied and widely disseminated material, and its principal applications are in gas sensors, transparent electrodes, catalytics, and optoelectronic devices. So, doping, zinc doping, and doping itself is used to improve some property of the material. So in this case, since I use zinc, the property I want to improve is the electrical one. And these are some figures about my EDS samples. They are just here to exemplification what the nanoparticle looks itself. Here the tin oxide group, tin oxide with zinc 5%, and here the tin oxide zinc 10%. So, the theoretical explanation of the method. In the synthesis, I utilize the sodium method, which is sometimes called the polymeric precursors. And here you have the representation diagram of the reaction mechanism. So the first thing you need to do is to make a solution with your metallic precursors. And the choice of them depends on what property you want in outputs to have. And after you make the solution, you do the chelated agents. This one, the function is to make complex with the use to evitate the precipitation. After that, you do the polymerized agents to form polymeric matrix with the complex to facilitate the formation of the reticulate material. And after that, you lead your sample to the drying to remove potential solvents or residual solvents. And after that, you lead them to the calcination, where you have the densification and crystallization of the product. Here you have the experimental procedure, and here you have everything that I already said, but the specific case of my synthesis. The precursor of tin is chloride, the precursor of zinc is zinc acetate, the chelated agent is citric acid, the polymerizing agent is ethylene glycol, and the only thing I didn't say in the past is this heating, and this function is just to facilitate the gel formation. And the calcination here I use is the 500 degrees to 700 degrees per 2 hours. So the characterization I use X-ray refractometer, which is XD, and CEDS. Here you have the results of my XD, and here you have the two. I want you to look at these two picks, and this more to the left, and this more to the right. This more to the left is the ZnO2 routine phase, and it's exactly what I wanted, but more to the right, we have a peak associated with the zinc oxide, and essentially it's not what I wanted. So here you have the EDS results. This one is just the base, the ZnO2 curve, and this others is with the zinc. So this one is 10, 5, and 10%, and here these zones with the red color is the zones with the zinc dopant. So our partial conclusions is the T-head analysis confirmed the metatonal phase routine of SNL2 NEL samples, and the secondary phase, the peak more to the right, was detected in all dopants, indicating the dopant concentrations exceeding the solubility limit, and the positive CEDS results confirm the presence and distribution of CN in all samples, validating the incorporation of the dopant into the synthesized material. These are my references, and thank you all very much.
Good morning, everyone. My name is Alexa, and I'm from Biopomat Group, University of Araraquara. My project focused on the hydrogel design for 3D printing of sensor scaffolds. This work is carried out under the supervision of Dr. Baruch. For this purpose, we combined cellulose nanocrystals, hyaluronic acid, and mexin to create a biocompatible, conductive, and stimulus-responsive material for application in regenerative medicine and smart biomedical monitoring. We chose cellulose nanocrystals because they adjust the hydrogel rheology very well, provide the necessary shear thinning behavior, are biocompatible, and disperse easily in water, contributing to creation versatile biowinds. Hyaluronic acid was chosen for its proven biocompatibility and also contributes to improving stability, mechanical properties, and discovery control during extrusion. Mexine was added because its bringing electroconductivity, high surface area, hydrophilicity, strong mechanical reinforcement, and good biocompatibility expanded the potential of the hydrogel for biomedical and sensing applications. To prepare my hydrogel, I used a speed mixer to mix and uniformly disperse the formulation containing the material in aqueous solution at both low and high mexine concentration and the carry of the 3D print. In the viscosity tests, we observed that the higher mexine concentration makes the structure strong and more reinforced. The amplitude with analysis showed that the linear viscoelastic region remained stable, indicating that the addition of mexine did not significantly affect the gel. The results of the storage and loss modeling showed that in all formulations, there is an elastic predominance and the material behaves as a stable gel. In the taxotropic analysis, the higher mexine concentration showed a recovery level sufficient to keep the material stable during extrusion. Here are images of the prints. In conclusion, the formulation exhibits pseudoplastic behavior suitable for 3D printing. The linear viscoelastic region remained stable. G prime remained higher than G double prime of samples, confirming elastic predominance. The 5 milligram per milliliter mexine formulation showed greater structure, reinforced and increased viscosity. This concentration exhibited relevant soluble recovery, being the most suitable for printing. Future work should include electrical conductivity tests to assess how well the formulation functions as responsive materials. Explore possible biomedical applications such as controlled drug delivery or smart welding dressing. Thank you very much.
Good morning, everyone. My name is Thais. I am a PhD in material science from SCAR. So, my work is chemical functionalization of bacterial cellulose from kombucha with potential for biomedical application. And my advisors in the France aula, in the Brazil, Daniel Comates and Professor Júlio. So, the main goal of my work is to produce kombucha from bacterial cellulose, IU abbreviation and CPK for better understanding, and the evaluation its potential for biomedical application in special and in dressing. So how do it? The first part, to produce or synthesize MCBK. In the second part, the functionalization on the surface of MCBK with amino groups, in special APTS, this is a presentation of this structure. And the last part, you'd like to incorporation antibiotic on the surface after the chemical modification. In this case, I use the Banco for to carry the antimicrobial properties. So, what motivation of my work? What the medical was must affected by antimicrobial resistance is yield healing. So, here are the maps. The first part is necessary to produce FCBK. I use normally green or black tea and sugar. And during the fermentative process, necessary to, in my case, variation date. The best date was the 21 days. And the second part for chemical functionalization, I use two different conditions with FTS. The first part, I use the solution FTS with 5-8%, and during the 24 hours. And the second condition, I use pure solution for immersion in the a little seconds. And the steps follow for the finalization part. And after the chemical modification, I use for this part for incorporation of vancomycin or vancomycin. I use 3 different concentrations: 1, 5, and 10 milligrams. And the step follow. And here I use this abbreviation for identify the samples. So in the characterization techniques, I use this FTR, elemental analysis, AFM, CAM, and the cell viability, and the others, but today's presentation is. So, speak the better day, 21 days, this case, this can be represented or occurring the reaction during the chemical modification. For to confirm this, introducing the special groups in the surface of the MCBK, spectra FAR confirm the main bands in special amino groups and selenium groups in the introduction in the surface in both conditions, the chemical modification, and this special bands presentation. So, the second elemental analysis, this table shows the higher or increasing nitrogen content in both conditions, the chemical functionalization, compared to pure MCBK. But the last condition in pure solution, two presentation, a higher nitrogen content and the gravity amount. So, and this is part in the morphological images for CM or AFM. The first morphological imaging is possible to observe the typical conservation of nanofibrils of the cellulose, bacterial cellulose, and that in the second condition is possible to exhibit the formation on a thicker layer, and in the last condition it's possible to observe the predominance of the structure the nanofibers. It's possible because the last condition because it's true success gravity of the chemical functionalization. So for the last years with about the introduction vancomycin, it's necessary to expect following this scheme for to expect this main reaction, amidation reaction, for during the incorporation of vancomycin. So for to confirm this reaction, spectra FAR should present the main bonds, the mini groups. So for to the last condition, this cellular viability was performed with periepithelial cells. So in all the samples exhibited no cytotoxicity, and the vancomycin did not affect cell viability. Just in this part in the low concentration pure vancomycin, start inhibition, this proliferation, but did not observe in the BCB with the same concentration because the continue to proliferation. So, and the conclusion of this work, so the biomaterials obtained present high potential for biomedical application, in special dressing. Okay, so thank you so much for your attention and special collaboration.
Good morning. My name is Cecilia, and today I present work developed by me and our research group, and a hybrid polymeric and biological scaffold for treatment of chronic wounds. So chronic wounds is a persistent clinical challenge. So opposite of acute wounds that have a cycle with hemostasis, inflammation, proliferation, and remodeling, and chronic wounds is stopped in the inflammation phase. So this fail the natural healing and the persistent phase of inflammatory, and turns chronic wounds a complex in treatment. So we suggest a hybrid approach combining polymer and biological scaffolds. So the 3D scaffold can have a physical support, controlled 3D architecture, and matrix extracellular from fibroblasts can give cell guidance and favorable environment for the regeneration of chronic wounds. So the polymer components of the word scaffold is PLDA Team C. We selected 1714 because it's similar to module elastic of the native skin and have biocompatible and biodegradable properties and favorite mechanical properties tailored. And this polymer is engineered with bio 3D bioprinting, so we can have a precise 3D architecture control. The biological components is matrix extracellular from fibroblasts and contain glycosamine glycanos and such hyaluronic acid, enzymes, and growth factors. These components give cell guidance, direct cell migration, and organization, and support the cellular viability in proliferation. So, as result, we have a morphology of polymeric scaffold and 4 millimeters per second impression, result in homogeneous pores with diamond symmetries. So this scaffold is cultured with fibroblasts, so it's functionalization. And here in third image, we have fibroblast deposited extracellular matrix forming a fibrous network in polymeric scaffold. And after the cellularization of scaffolds, we also have extracellular matrix components. So we have glycosamine glycans with evaluated by Alcian Blue methods, and maintain these components important for hydration and support our migration and proliferation. And we have high production of collagen evaluated by Cyrus Rex. And collagen is produced tissue strengthened and structure and crucial for chronic wounds healing. So we have a 3D printed created scaffold with uniform parts and controlled morphology. With successful functionalization, the scaffold is integrated with biological matrix with polymeric matrix, forming a hybrid material, and the 3D printed scaffold promote higher matrix deposition. I want to thank you, my research team of the Biomaterials Laboratory of São Paulo, and the CAPS that supported this project, and thank you all of you for attention.
Pessoal, muito obrigado por estar aqui, né? Esse horário, passando um pouquinho do horário. Então, se o professor João não for, poderia começar a falar também os 14, posso essa cor de 20, 30, pode ser?